everyone.
So yeah, we have Carolina Araujo who will tell us about blow-up, scale, duality, and moduli spaces.
Okay, thank you. So first of all, hello everyone. Good morning good morning for me. This is 10 a.m. in Brazil right now. I wish we were all together having a Blackboard lecture, but unfortunately this is not possible at the moment. So maybe before I start, I just wanted to invite whoever feels comfortable to just turn on your video so that I see my audience. Okay, so this is much better now. Okay, hello everyone. So I will now, so this is going to be a series of 4 lectures, and I think they will be slightly under 1 hour so that we don't get tired, but please do interrupt me if you have questions, and then I can even try and share my, tablet. Okay, so now let me start sharing my presentation. And I was really hoping to give this as a Blackboard talk, so I have it. Okay, so I have sort of written it up. So the idea of this this mini course is to discuss blowups. So this is going to be the topic of the first lecture, and then Gale duality and moduli spaces, and this is going to be we're going to discuss this later on in the week. So the lecture today covers a very classical and basic material, that of blowups of the plane on points. So here, oops, sorry. Here is the setup. So we are going to be working with a set of m distinct points in the complex projective plane, CP2. So we always work over the complex numbers. So many of the things that I will say, they are still valid over other fields, but I am going to stick with the complex numbers for simplicity. So in general, we will start with a set of distinct points, and then we just blow up this point. So this provides a birational proper morphism from S. This is how I denote the blow up of P2 and M points to P2. And the usual notation here is the following. So I will denote by H, the pullback of the line bundle OP21. So as usual, I do not distinguish between line bundles and the visor classes. And I will denote by EI the exceptional curve over the ith blown up point. So this is a curve that is birational, that is isomorphic to P1. And then the Picard group of the surface S is generated by the class of the pullback of the hyperplane section and the class of the exceptional divisors. And we also have the intersection pairing on the surface that is given by this formulas. H squared is equal to 1. H intersects EI in 0. Each exceptional divisor has -1 self-intersection, and the exceptional divisors lying over different points, they do not intersect. So this is the usual intersection form on the blow-up. Another object that is going to be important here is the canonical class of the surface, which is, as usual, we can write it as 3H minus the sum of the EIs. Yes? Hello? Is there any question? Okay, so, and also we will often, instead of just considering the Picard group, we will often transfer by the reals and get a real vector space of the dimension m+1, which is what we call the Néron-Severi space of the surface S. Okay, so here we usually have an intersection form in this real vector space. Okay, and here is there's the very rough trichotomy that we get in the two-dimensional case is the following. There is a natural subdivision into 3 cases. The cases when you have at most 8 points, And then there is a special case when you have 9 points in P2. And then when you have, sorry, here I should have M. I was calling the number of points M. And when M is at least 10, we get a different situation. So roughly speaking, the first case, K less M less or equal than 8 is a finite case, as we will see. The case when K equals to 9, this is an infinite situation, but where we still have some order. And when the number of points is greater or equal to than 10, then you have an infinite behavior and wilder behavior. So this corresponds to the behavior of the canonical class. So when the number of points is at the most 8, then if the points are in general position, I will say exactly what I mean by that soon, then the anti-canonical class is ample. And so this is what we call del peso surface. In the case when K equals 9, then the anti-canonical class is no longer ample, but it's NIF. And here by NIF, I mean that a divisor on a surface is NIF, it intersects every curve non-negatively. So this is the notion of a NIF divisor. And moreover, the anti-canonical class in the case of 9 points is NIF and effective. So we can always find a cubic curve that passes through the 9 points. And then in the third case, the anti-canonical class, when you have the more than 10 points, it's no longer NIF, and also that also changes the behavior of the surface. Okay, so now let's look at some concrete examples. So let's start with 1 point. So we fix we fix 1 point, and then up to automorphism of P2, we may assume that this is the point with coordinates 1, 0, 0. So there's no moduli here for a small number of points. You can always choose it to be this point. And then in this case, the Néron-Severi space of the surface is two-dimensional. So it's generated by the pullback of the hyperplane section and the exceptional divisor over the unique point P. And now here I will introduce a new character now, which is this what we call the cone of curves, or the Mori cone of the surface. So as usually this will be inside the Néron-Severi space. This is defined as the closure of the set of non-negative linear combinations of classes of irreducible curves. So we take some finite effective linear combination of curves, but then we usually have to take the closure of this cone to get something closed in this case, in this R2. And so this is usually called either the Mori cone of the surface S or the cone of curves of S. And in this specific case, when we blow up 1 point, then this is a very simple cone. This is a closed convex cone in dimension 2. There's not much that you can do. You always have 2 rays that generate a cone. In these cases, the cone is generated by 2 rays. The ray given by H and the ray given by E. Okay, so this is in this case we have two extremal rays. So I draw one of the extremal rays of the cone. I draw it in blue, which is the ray spanned by the class of the exceptional divisor E. And notice that this in this case, we have this morphism pi from S to P2 that contracts the exceptional divisor E to the point. And this is what we call the contraction of the ray in the following sense. This is a birational morphism that contracts a unique curve E to a point. And this unique curve that gets contracted by this morphism is a curve whose classes lies in the extremal ray. So this is what this picture is illustrating. And now if I look at the other extremal ray of this cone, so this is now the one that is generated by H, it also admits what we call a contraction in the following sense. So we have this So now I wrote a diagram, this diagram to the right. So I have the pi p is the projection from the point P to P1. So this will usually is not defined at the point P, and it contracts the lines through the point P to the different points of P1. When we blow up the point P, we resolve the indeterminacy of the projection from P, and so we get this morphism that I denoted by F from S to P1. And notice that this projection F, the map induced by the projection from P, it contracts precisely the strict transform of the lines to the different points of P1. So again, the only curves that are contracted by these morphisms are those curves whose class lie in the ray generated by H. So again, this is what we call the contraction of an extremal ray. Okay, so in general, now, before we look at the case 2, so again, if I take a set of 2 distant points in P2, then again, up to automorphism of P2, I can assume that my points have coordinates 1, 0, 0, and 1, 0, 1. My points are always distinct, so I can assume that these are these points. And again, here, the Néron-Severi space is generated by these 3 classes, the pullback of the hyperplane section, E1 and E2. And we will want to describe the cone of curves or the Mori cone in this Néron-Severi space. Okay, so before I describe this one explicitly, let me just say some generalities about the Mori cone. So usually we say that array of the cone, so now as soon as I have I am in a Néron-Severi space of dimension at least 3, the cones are going to become more complicated. In the 2-dimensional case, you only had 2 rays, and so there's only 2 possible extremal rays. In general, there are many more possibilities. So we say that, so first of all, a ray in our cone is an extremal ray, and this is what we, intuitively, what you think we can think of. We can define it in this way. An extremal ray is a subcone of my cone with the property that if I have 2 elements in the cone that add up to an element in the ray, then the elements U and V are already in the ray. So for example, so this is an easy exercise. If you have a -1 curve on your surface, by a -1 curve, I mean a curve C that is isomorphic to P1 and whose self-intersection is -1. So if this is a -1 curve, then you just easily compute that it is an extremal ray of the Mori cone. So if you have never done this exercise, I invite you to do this. And in this case, such an extremal ray can always be contracted. So this is the content of Castelnuovo's contractibility theorem that says that whenever you have a -1 curve C on a surface S, then this surface S can be written as the blow up of another smooth surface S prime along a point Q. And under this isomorphism, the -1 curve C corresponds to the exceptional divisor of the blow-up. So this is the concept of Castelnuovo's contractibility theorem. And now going back to our example, when we have 2 points with coordinates 1, 0, 0 and 0, 1, 0. Now here, well, we have, okay, of course we have this, the extremal rays determined by E1 and E2. But now we found some new extremal rays that maybe you did not notice at first. So if you take the line L connecting the points P1 and P2, and you look at the strict transform of this line, then you get this curve, which I denoted by L tilde. And now you can compute the, so this, of course, this L tilde is isomorphic to P1. And moreover, you can check that it's linearly equivalent to H minus E1 minus E2. So if you take a line that passed through P1 and P2, and you look at the strict transform, its class is going to be the pullback minus the E1 and E2. And so you compute and you see that the self-intersection is -1. So by Castelnuovo's contractibility theorem, this generates an extreme array that can be contracted. In this case, one can show that the Morricone is spanned precisely by these 3 extremal rays in red, blue, and purple. So these are the 3 extremal rays of the Morricone, and each one of them can be contracted to a surface. So if you contract either E1 or E2, then you go back to P2 blown up at only 1 point. And if I contract the extremal ray generated by L tilde, then what we get is a morphism to P1 cross P1. So this is again the classical statement that the the quadric P1 cross P1 blown up at 1 point is isomorphic to P2 blown up at 2 points. Okay, so now this is okay. So this was when we have 2 points, and now when we have 3 points, then now we start to have non-isomorphic possibilities. In this case, we have 2 non-isomorphic possibilities. The first case is when the 3 points lie on a line. And the second case is when the 3 points do not lie on a line. So they can be thought as the vertices of the coordinate triangle. Okay, and let's look at what happens at these 2 cases separately. So in the first case, we can look at the strict transform of the line that passed through the 3 points. So this is what I'm calling L tilde. And you can compute again using the intersection form on the blow up. You can compute the self-intersection of L tilde, and you will get that this is -2. Again, in this case, of course, this is not a -1 curve, so we cannot contract it to a smooth curve. But still, whenever you have a curve with self-intersection -2, it can be contracted to now a singular surface, but it's still a surface with a dual singularity, with a double point that locally looks like the cone of the vertex of a quadric cone. And so again, in this case, you can check that the cone of curves has 4 extremal rays generated by the strict transforms of E1, E2, and E3, and again, the strict transform of the line through the 3 points. In general, we will be considering point sets that satisfy some genericity, some generic position. So we will not be looking in general at sets of points, for instance, all line on a line on other some other special configuration. So here, this would be the second possibility when we have the 3 points, and then again, up to automorphism of P2, we can assume that our points P1, P2, and P3 they are the coordinate points of P2. Okay, and then in this case, then let's blow up these 3 points. Then again, when we blow up the 3 points, we get 3 -1 curves, E1, E2, and E3. Sorry, here sorry, it would be E3 in the green one. So we have this 3 -1 curves. But again, if you look at the strict transforms of the line passing through 2 of the 3 points, again, you compute its self-intersection. And again, this is going to be -1. So we have this 3 -1 curves, which are the strict transform of the lines. And these are disjoint -1 curves. And then again, we can use Castelnuovo's contractibility theorem to conclude that we can contract these 3 -1 curves, the strict transforms of the lines, again, to 3 smooth points on the surface. So this diagram that I drew here is nothing but the resolution of the standard Cremona transformation. So if you take the birational map of P2 to P2 that is given by this expression, YZ, XZ, and XY. this is a birational map that is not defined precisely at the 3 coordinate points. It contracts the coordinate lines to the opposite coordinate point, and it is a birational involution. And this is resolved precisely by this three-point blow up. Okay, so here, in this case, what we notice is the following, that so if you take, so here, what I drew here, so if I started with 3 points, P1, P2, and P3, I blew up, I got to my surface S. And there, I have 2 different ways of realizing my surface as a blow up of P2 in 3 points. The original one that I gave you, and then I could also, the second one is given by the contraction of the strict transform of the lines. So that is to say, given the surface abstractly, there is no natural structure morphism as a blow up of P2 in 3 points. There is a choice here. In this case, I could either choose the 3-1 curves to be E1, E2, or E3, or the strict transform of the 3 lines. And in general, if I take, oh, sorry, I think I wrote something in Portuguese here. If I take C, a curve of degree D with multiplicity Mi at the point Pi, then I will denote this strict transform C tilde. So this is a curve that in the Picard, its class in the Picard group is DH minus M minus sum of the MIEI. So this is the class in the Picard group of the strict transform of the curve C tilde. But notice that I could have chosen, instead of the first realization as a blow up, I could choose the second realization of the surface as a blow up of P2. And then this would give me a different basis of the Picard group, which I'm denoting by H prime and then EI prime. And these are related, so these are different bases for the same Picard group or for the Néron-Severi space. And the change of basis can be given in terms of these roots. So the H prime, say if I take the pullback under the second blow up of a hyperplane section here, well, this is, if you remember, this has been just given by the Cremona transformation. This would be just the conics. So this is 2H conics that pass through 3 points P1, P2, P3. So this is the pullback of H under the second projection. And then when I look at the exceptional divisor EI for the second projection, if you write it in terms of the first basis, this can be written as the strict transform of the line passing through 2 of the points. So this is why it has H minus EI minus EJ. So this is to say here, I have so this again, this is what you should keep in mind from this example, is that if you blow up 3 points in general position, then there are 2 different ways of realizing this as the blow up of P2 in 3 points. And so I have a choice of bases here. Okay, so, and in this case, you can again show that the cone of curves of the surface is generated precisely by this 6-1 curves. And let me now state a general theorem. So now I will take a set of points P1 up to Pm in P2. And I will assume the following. So first of all, now let's assume that we have already considered the case when we blow up 3 points. So let's assume that we always have at least 3 points and we have at most 8 points. And let's assume that they're in general position. And to be very precisely, what I mean by this is the following. So first of all, I assume that no 3 points lie on a line. No 6 points lie on a conic. And I also assume that there are no rational cubic curves through 8 of the points. So if I have this configuration set, then the conclusion is that, first of all, The anticanonical class is ample. So this is what we call a del Peso surface. Moreover, there are finitely many ways of realizing this surface S as a blow up of P2 at endpoints. So I will denote it in this way. So there are morphisms from S to P2 that contract certain curves that I will denote LIP to some points PIP. So this is, so there are finitely many ways that I can write my S as the blow up of P2 and endpoints. And in particular, the Morricone of the surface is generated by finitely many -1 curves. And conversely, actually, there is a converse to this theorem that any del Peso surface, meaning a surface for which the anticanonical class is ample, a smooth surface for which the anticanonical class is ample, can be realized as the blow up of P2 in at most 8 points in this satisfying these conditions. Well, either this or the surface is P1 cross P1. But in a sense, there is this this converse. So this is the first case that I explained, the case when we have finiteness. At most 8 points, then you have the anticanonical class is ample. There are finitely many blow up realizations as a blow up of P2 in endpoints, and there are finitely many -1 curves. Even we can, and this is classical again, you can even write down what are the -1 curves on this blow up. So let me just go through the list very quickly here. So there are the EIs. So the EIs are just the exceptional divisor of the points. Then these are the ones that we have seen already. So this is the strict transforms of, so H minus E1 minus E2. These are the strict transforms of the lines passing through 2 of the points. Then you have these ones here. This is the conics passing through 5 of the points. If I look at the strict transform, again, this you can compute. This is again a -1 curve. And then you have this cubics here. So you take, so now we have here, we have to have at least 7 points. And then I take cubics that pass through 7 of the points and has, it's a double at one of them. So it has to be a nodal at one of the points and passing through 6 of the other points. Then we have the quartics that are passed through the 8 points and are double at 3 of them. Then we have the quintics that pass through the 8 points and that are double at 6 of them. And finally, we have the sextics that pass through the 8 points, double at 7 of them and triple in 1 of them. So you can, if you can compute, so first of all, you have to show that you can construct each of these curves. And then once you construct them, you can, and I will explain you how to do this. And then after you construct them, you can use the intersection form to compute its self-intersection, and then you see that these are -1 curves. Okay, so these are the -1 curves on the del Peso surfaces, and it's okay. So, and now let's start to look what happens when you take more. What happens when you take more than 8 points. Okay, so now let's assume that we have endpoints P1 up to PM in P2. Now assume we have at least 9 points. And again, we always assume that these points are in general position. So no three points lie on a line, no 6 points lie on a conic, and no 8 points lie on a rational cubic curve. If you have this, then the conclusion is that then there are infinitely many -1 curves on S. And well, so these are the ones that we already had before, but we can write down more. And let me explain to you a construction. So this is how you can construct -1 curves of arbitrarily large degree. So suppose that you have already constructed a -1 curve, which I am calling C tilde, which is the strict transform of a rational curve of degree D passing with multiplicity AI through each of the points PI. So this is the class of my curve. And so suppose that I assume that we know how to construct curves of degree at most at least 6, and I will order the AIs so that they are in their increasing order. And now I will explain to you how to, starting from this curve C tilde, assuming that we have at least 9 points, we can construct another -1 curve of degree higher than D. And this is what we will do. So I take my curve C. Well, actually, I take the curve C on P2, the curve, rational curve passing through the points, each of the points PI with multiplicity AI. And now I take, and what I do is the following. So I have, or let me, up to change of coordinates, I can assume that the first 3 points, the ones with smaller multiplicity, are the ones with coordinate points 1, 0, 0, 0, 0, 1, and 0, 1, 0. And now let me do the standard Cremona transformation based at these 3 points. So if I do the standard Cremona transformation, then the curve that I obtain in this way, the curve C prime, then this is an easy computation using those change of change of basis that I explained earlier in the case of the blow up at 3 points. You can write down the image of this curve C under the Cremona transformation. This will be a curve of degree D minus A1 minus A2 minus A3. So the degree changes in this way. Now, the new coefficient, the new multiplicity at the point P1 is going to be D minus A2 minus A3. The new multiplicity at the point P2 is D minus A1 minus A2. And then the new multiplicity at the point P3 is minus A1 minus A2. And the other multiplicities are the same. And now the observation is that if you started with a -1 curve, then necessarily, and this is an easy computation, necessarily this number D minus the smallest multiplicities must be greater than D. So in other words, if you compute if you look at this C tilde, you assume it is a -1 curve, so you know that its self-intersection is -1, and its intersection with the anti-canonical class is also -1, and then you compute, and then you easily get this, this is what we call Nether's inequality. And so in this way, we construct a -1 curve that has degree greater than D. And this is how you show that there are infinitely many -1 curves. Okay, so maybe I would like to explain again, it may look like a bit of magic, how come suddenly when you went from 8 to 9 points, you found infinitely many -1 curves. So there is something hidden here that I would like to make a little bit more explicit, which is the action of a group, a Weyl group, which is infinite when we blow up at least 9 points. So let me make this more explicit. So again, let me take the surface S, the blow up of P2 at these M points. And again, I recall what is the anti-canonical class. And now I will construct a group as follows. So let us consider the orthogonal complement of the anti-canonical class. So this is the subgroup of the Picard group, consisting of classes that intersect the anti-canonical class in 0. So this is a lattice ZM, and I can choose a basis alpha 1 or alpha naught up to alpha m, and I will choose this basis as follows. So I leave you as an exercise to show that this is in fact a basis of this orthogonal complement. So alpha 1 is E1 minus E2, alpha 2 is E2 minus E3, and so on, up to alpha m minus 1, which is the EM minus EM minus 1 minus EM. And then the last element of the basis is this one that I choose to be H minus E1 minus E2 minus E3. I choose three of the exceptional divisors. And now I will construct what we call the Dinkin diagram associated to this. This is a root system. And we check that each one of these generators have self-intersection -2. And I will construct a Dinkin diagram associated to this root system by connecting two nodes, if and only if the elements out. So I connect the nodes corresponding to alpha and beta, if and only if the intersection number of alpha and beta is non-zero. So in this case, we get this here. I'm assuming that M is at least 5, so that this makes sense. So I get this Dinkin diagram, which has this shape. So you check. I leave you as an exercise to check these intersection numbers. And then you get that. So this is the Dinkin diagram associated to this root system. And now I will consider for each one of the roots alpha, I will consider the reflection around alpha. So this is if I draw alpha defines a hyperplane, and I reflect with respect to this hyperplane. So this can be given in terms of in linear algebra by this formula. The reflection of V is V minus the V intersect alpha times V. And if I now consider the group of reflections that is generated by this, each one of these reflections are alpha I. This is a group. So this is a group. This is contained in the orthogonal group, in the group of symmetries of the orthogonal complement of the anticanonical class. So this is this group of reflections. It can be, this is what we call a Coxeter group, which can be abstractly described as follows. So this is a group that is generated by M elements. So these are this is a presentation for this group. So this is generated by S1 up to Sm. Each one of the SIs is an involution, so SI square is 0. And then moreover, we request that the product S alpha dot S beta has order 3 precisely when alpha and beta are connected in the Dinkin diagram. So this is a Coxeter group. And so this is a very well-known group in group theorem. And it is a fact that this group is finite if and only if M is at least 8. So as soon as you have more than 8 points, when you have 9 points, then when you look at the group generated by these reflections, this is as an infinite group. So this is precisely why we could, when we had 8 points, we could perform enough Cremona transformations in order to construct -1 curves of arbitrarily large degree. And so if you look at this group, if you forget about the alpha 0, if you look at the group generated by the reflections along alpha 1 up to alpha m minus 1, this would give us exactly the symmetry group. So this would be corresponds to the permutation of the m, in this case, m minus 1 points. sorry, this is the permutation of the m points. And when as soon as you add the reflection with respect to alpha I, then what you do is you perform a Cremonez transformation centered at the 3 points P1, P2, and P3. And so when we were saying that you can act by this group, so basically what you say, you make a permutation so that you assume that the multiplicity of the curve at the points is in increasing order. So this is what we did in the beginning of the proof. So we made a permutation so that the A1, A2, and A3 are the smallest ones. And then we did a per Cremonez transformation. So this would be just a reflection with respect to alpha naught to create a curve with higher degree. So this is how the infiniteness comes to play in a more explicit way in the proof. Okay, so let me just finish by discussing the cases in a little bit more details, the case of m equals to 9 points and at least 10 points. Okay, so the case when m equals to 9, in this case, the anticanonical class is sniff and effective. In this case, so as I said, you can always choose a cubic curve passing through the 9 points. And so this anticanonical class has self-intersection 0. So this is an easy computation. And so when you look at the Morricone, as we have seen, it has infinitely many, it's generated by infinitely many -1 curves. And when you take the closure of the Neff cone of this -1 curve, then you get the full Morricone. So this is the picture that you get. So you get this, the ray generated by the anticanonical class is an accumulation points for the extremal rays. And all the other extremal rays on the negative side of the canonical. So I draw here. So here I illustrated the canonical class defines a hyperplane in the Néron-Severi space. So I denoted by plus the half space of points with positive intersection with the canonical, and minus here the size of the size of the Néron-Severi space with negative intersection with the canonical. And the cone, the Morricone in general, is going to be, well, there is the side on the negative part of the hyperplane. It's always generated by locally discrete extremal rays. These are generated by -1 curves. And then you have this accumulation point here. Actually, it's an interesting problem. This probably using the Vio group that I explained in the previous slide, one can compute this. It would be interesting to find a fundamental domain, a polyhedral fundamental domain, such that when you act by this infinite discrete Vio group corresponding to m points, then you get the full Morricone. So this is I leave you as an exercise to find out what is this polyhedral fundamental domain under which the Vio group acts to cover the whole Morricone. And then in general, when you have at least 10 points, then now the anticanonical class is no longer Neff. And again, we have the cone theorem that says the following. So I will describe the Morricone in this general case. And in general, there are 2 sides of the cone. So I can divide my space, my Néron-Severi space in the half space of points having positive and negative intersection with the canonical class. And what the cone theorem, this holds for any surface S, what it says is the following. So on the half space of negative intersection with the canonical, the Morricone has locally discrete extremal rays, and each of these extremal rays is generated by the class of -1 curve. So these are the extremal rays. This is the behavior of the cone in the negative side of the canonical. Well, and we don't know how the cone looks like on the positive side of the canonical. So this is this shaded region here is we usually do not know the shape of the cone. So this is expected to be a round cone like this, but it's true that this is the truth is that this is not known. And so let me end this lecture with a conjecture. So this is what is called the Nagata conjecture, which gives some information about the shape of the Mori cone on the other side. So it says that if you have a curve in the Mori cone, so that this is the strict transform of a curve of degree D in P2, passing multiplicity AI of each of the PI. So this is the class of the curve in the Picard group. If this is the class of a curve, then these coefficients DI and AI must satisfy this condition here. So this is what is called usually the Nagata conjecture. And when Nagata stated this conjecture, he proved this in the case where the number of points was perfect square. And so in this case, this inequality is verified. But in general, it is still an open problem to show this condition here. Okay, so this is what I would like to discuss today. So this is just the recollection of the classical theory for a blow up of P2 at finitely many points. And then tomorrow we will leave the plane and move to higher dimensions Pn, and then we are going to start looking at the geometry of the blow up of at Pn in a certain number of points. Okay, so I stopped. So this is how I finish my first lecture. Let me stop sharing here.